The noise that airfoils produce is much more important than we usually think. For example, the noise that wind turbines make largely comes from their blades, which are airfoils, and this noise is actually quite famous because it severely affects some people, and then other people barely notice it. Another example of airfoil noise is airplanes. So when you hear an airplane landing, much of the noise is coming from the wings along with other structures like the landing gear. And it might seem a little strange to think that airfoils produce noise, because the flow over airfoils usually is quite well behaved. But there are two main regions of noise production on an airfoil, the leading edge and the trailing edge, and every airfoil has these two regions. So reducing the noise that airfoils make can be very beneficial for the operation. So coming back to the wind turbine example, quieter wind turbines means you can have more of them closer to where people will live, which means that you can have more room to put them, as well as even put more of them around. So while we can hear the benefits to quieter airfoils loud and clear, how can we reduce their noise? That is what we're looking at today. So we're looking at how to make the trailing edge of an airfoil that is serrated, how that affects the noise produced by an airfoil and why. So to look at these effects of these serrated trailing edges, we have this paper called Aeroacoustics. Let me zoom up, scroll up here. Aeroacoustics of Sawtooth Trailing Edge Serrations Under Aerodynamic Load. So this is an open access paper, and you can find it in the link below if you want to play along at home. So out of all the things you could do to an airfoil in an effort to reduce its noise, why make the trailing edge serrated? What is the idea behind that? Well, perhaps the most famous instance of a serrated trailing edge is owl wings. So owls, their wings are very, very quiet, and we actually went through owl wing noise production and the general aerodynamics of an owl wing in podcast 176. In that podcast, we saw that the owl wing in general are super quiet, like they're down to like 20-25 decibels, almost nothing. And that is in at least part due to the serrations that it has on the trailing edge of their wings. In this podcast, we're going to go further and look at how serrated trailing edges affect airfoils in general, and not only in terms of noise production, but also the flow physics involved. So this is actually a very important distinction to make, because owl wings that we make are not the same as bird wings really. While bird wings, including owl wings, flap their wings to fly, we don't use our wings in that way. Our wings are stationary, and as a result, the flow physics you see over our wings is very different to a flapping wing. So do serrations work on our own wings, like human wings, and how do they work? So in this study, the researchers used 3D PIV, so you can actually reconstruct the entire velocity field from this technique. It's really cool. Because like regular PIV is only 2D, and with that type of PIV, you can only see you can only have one plane going through, and you can only see either 2 or 3 components of the velocity at that plane. With 3D PIV, you get far more information, and you can see where the flow goes in this volume in time and how it evolves. So for this study, they had a flat plate with the trailing edge able to deflect up or down by plus or minus 15 degrees. The flat plate had an elliptical nose, which is most likely to reduce the impact that the start of the flat plate has on the air flowing around it. And this is actually very common to have a nose with this elliptical shape for splitter plates. And a splitter plate is used in a wind tunnel to effectively get rid of a boundary layer that has been forming and have a fresh flow now hitting the object that you're interested in. So one common example is when you have, for example, a wing from an airplane. If you have just like a massive wing and you don't have the airplane itself and you attach it to the floor, well, if you have the flow going along the floor in the wind tunnel, by the time it hits the wing, you have a boundary layer forming. That may approximate a fuselage boundary layer, maybe not, maybe you're not interested in that either. So what you would do is you would then elevate the wing off of the boundary layer, maybe a foot or whatever. Then you put a splitter plate underneath the root. So now you have a distance between the floor in the wind tunnel and the splitter plate, and you have a fresh flow hitting the wing now. So that is a general elliptical nose that they have on this splitter plate as well, on this flat plate, I should say. So also, they say that they use turbulence generators near the leading edge, as we can see in figure 1 here, in figure 1C, and they wanted to make the boundary layer turbulent with them, evidently. So they say that the trailing edge serrations also had an amplitude of 60 millimeters, so from the start to the end, 60 millimeters, and a wavelength of 30 millimeters, so 30 millimeters wide at the start of them, and then it goes down into a point. So the experiments were done at 10 meters per second, which gave a Reynolds number of 670,000. Now in table 1, we see some really cool data. So they first of all give something called the shape factor. And if you don't know what the shape factor refers to, check out the video on our YouTube channel called Aero Fundamentals number 38, Boundary Layer Shape Factor Explained. In a nutshell, the shape factor gives a good indication as to whether a boundary layer is turbulent or not. It is based on the boundary layer displacement thickness and the boundary layer momentum thickness, which we have also covered both of those topics on our YouTube channel as well. Anyway, as a general rule of thumb, if the shape factor is 2.6, about that, then we consider the boundary layer to be laminar. So we have the shape factor here. And if the shape factor is around 1.3-ish, then we consider the boundary layer to be turbulent. Now, this is an incredibly powerful tool because boundary layer profiles are very subjective, or at least to some extent. So by being able to reduce the profile effectively to just one number, it makes it very easy to compare. Now we come to something interesting about this table. So if you look at the shape factor here, let me zoom in a little bit actually so we have a better view. So the shape factor is just here. So if you look at the shape factor, we see that when the flap is deflected by different amounts, so either 0 degrees, 10 degrees, or 10 degrees on the pressure side, the numbers change. So when the flap, which here is just a straight trailing edge, is completely down, so it isn't deflected, it's completely flat, so it isn't deflected up or down, the shape factor is 1.39. That means that the boundary layer is almost certainly turbulent. I mean, it's very close to 1.3-ish, so that's very close to being turbulent, if not absolutely turbulent. So that isn't surprising considering that they used these turbulence generators upstream on the airfoil to induce this transition to turbulence. So now when the flap is deflected up by 10 degrees, the shape factor changes to now 1.44. It is a bit of a jump. It isn't that big, but it shows that the boundary layer does change when you deploy the flap up or down. Now, when you deploy the flap down by 10 degrees, the shape factor now drops to about 1.29. This again shows just how sensitive the boundary layer is to the flap angle. And looking at the boundary layer displacement thickness and momentum thickness in this table, we see that likewise, the flap angle affects these quantities. So we have the displacement thickness here and the momentum thickness here. And just the plain old boundary layer thickness is also affected up here, with the general trends being more that when the flap is deflected more upwards, the thicker the boundary layer becomes. In fact, between the two extreme angles of minus 10 degrees and plus 10 degrees, the boundary layer thickness changes by 15%. That is significant because that also affects the flow attachment and how willing the boundary layer is to stay attached. So they also have other really cool data on this table. That is the pressure gradient along the flat plate with the trailing edge of flap deployed at different angles. This pressure gradient here. This is really cool and it is incredibly rare to find this kind of information. Like if you were to try to find this information in a textbook or something, you might struggle to find it. So having a paper here, which isn't actually really on boundary layers, but still included, this is quite thorough. So anyway, as expected, the more the flap is deflected upwards, the greater the pressure gradient becomes against the boundary layer. So when the flap is deflected at 10 degrees down, the pressure gradient is minus 53.9 pascals per meter. What that means is that every meter you travel downstream along the plate, the pressure drops by 53.9 pascals. That is a very favorable pressure gradient because it helps keep the boundary layer attached. Alternatively, when the trailing edge flap is flat, the pressure gradient is now minus 8.5 pascals per meter, which is still good because it is negative and that helps keep the flow attached still. But now when we deploy the flap at 10 degrees up, the pressure gradient now jumps to 45.9 pascals per meter, which means that there is now this back pressure acting on the boundary layer, trying to decelerate it. That will result in the boundary layer separating sooner because the boundary layer is now having this force pushing against it and reducing its velocity and then resulting in reverse flow and then it lifts off. So with this general information, we have a very clear picture of what the boundary layer looks like and the conditions it is subjected to. This is incredibly thorough to get all this information about the boundary layer. Let's now jump to the PIV section. So in figure 1a, we see the general angle of the PIV setup. So in the green light region, this green light being shown here, this is a laser sheet shining straight through. You can kind of see the serrated edges going here. They're like illuminated in white. I guess that's like a reflection kind of thing. Then you have the camera at about 45 degrees to the laser. I guess there might be another camera or a couple cameras behind this that we can't really see. But anyway, in table 2, we see information about their PIV setup. So just here. So the frequency of their PIV of the camera at least, was 5,400 Hertz, which is quite impressive for a 3D PIV setup. I mean, there are some PIV systems which are 2D that are only in the hundreds or even tens of Hertz range. So this one being 5,400 is very good. I mean, I remember actually when I was learning PIV to begin with, the first system I was on, it was like, I think like 10 or 20 Hertz. It was really slow. So now you can get into hundreds of kilohertz and that, but they're very complex. So having a 3D PIV system at 5,400 Hertz is pretty good. In terms of the resolution, they say that there are 10 pixels for every millimeter. Now, this is something important here. When we say 10 pixels per millimeter, we don't actually mean that the resolution is now 0.1 millimeters, because it depends on something called the interrogation window, traditionally at least. So in PIV in general, you break up the picture that you take with the camera into things called interrogation windows. And what you do is you look at what the particles in this window are doing in general. So to give you an idea, common interrogation window sizes are 16 pixels by 16 pixels, 32 pixels by 32 pixels, 64 pixels by 64 pixels, and 96 pixels by 96 pixels. And because even for the 16 by 16 pixel interrogation window, there are now 256 pixels in this window, 16 times 16. Well, with a window even that small, there are likely going to be several particles that you're capturing. So you are taking a general average of what is going on in this general window, and then you say, okay, in this region, which is 16 pixels by 16 pixels, the flow is moving in this direction, and you put an arrow in that direction. Now, that is the typical way of processing PIV results. The authors here seem to have taken a different approach, though. They say that their spatial resolution is effectively 2.5 millimeters, and they effectively chose this value because they wanted this resolution to be 1/3 of the particle mean distance. So they based their resolution on the actual particles and not on the number of pixels that they have in the camera. That is a very interesting way of doing it and not very traditional at all. And actually, I'm a little bit confused about how they would do this accurately, because to know what the particles are doing, you first have to process the results, which requires you to choose their interrogation window size or make a guess about how fast the particles are traveling. In the latter way, I guess you could then do an iterative process where you would make an initial guess, see what the results are, and then refine the guess again and again and see how the results change. Anyway, I like the interrogation window approach better. But anyway, in table 2, they also give the uncertainty in the velocity measurements, which is a really nice addition that you don't often see. They actually calculated the uncertainty in the PIV measurements. They calculated it to be 0.04 meters per second, which is 0.4% of the free stream velocity. That's pretty low. Now, in addition to PIV, they also added pressure sensors to the serrated edges, the trailing edges, to see what the pressures were doing there, as we see in figure 2 here. And I really like how thorough they are here, because with PIV, especially 3D PIV, it gets so much praise and has this like la-di-da reputation. But PIV is still just giving you velocities. You can't get pressures directly from PIV. You can try to calculate them, but that is quite erroneous. So adding in actual pressure measurements is way better. So in figure 2, we see where the pressure sensors are installed, and they're along the trailing edge of the serration and in the middle. In table 3, we see the uncertainties of the pressure sensors. So here's table 3. They say that they have an uncertainty of 0.02 pascals, which is the equivalent of 0.5 decibels. And that is for a 95% confidence interval. And I must say that they have done a really good job in quantifying the uncertainty in their experiments. It is rare to see so much work put into this aspect of experiments. So in addition to the PIV and the pressure measurements, they also did something called beamforming. So beamforming is just a fancy term for effectively triangulating noise sources with multiple microphones. So to locate a source in a 3-dimensional space, you use these different microphones located around, and you see how they correlate in terms of the noise coming along there and the frequency of them. So it is a really cool technique. In figure 1b, we see their setup, and from what I can tell in figure 1b here, let's scroll across some. So this is their setup here. From what I can tell, It is a curved line, this apparatus, with a bunch of microphones sticking up out of it, and it's located above the plate, I think. It's either above or below. I guess I could move it either side. And then in the background, we see there's an anechoic chamber or a wind tunnel with all these like sound-absorbing materials. So with that, we have covered the methods. So let's jump to the results now, because there are some really juicy findings. Let's zoom out a little bit and go to figure 3. So in figure 3 here, that's figure 4. Here we go, figure 3. I can count. Okay, so in figure 3, we see the noise being produced by the plate with the trailing edge being straight and serrated. In this figure, the dashed lines are serrated counterparts to the straight lines. As a side note, I really like this graph because of the way that they have decided to represent the information. It is very easy to keep track of. So the same color means that the flap is deflected at the same angle. So it is very easy to compare the straight trailing edges with the serrated trailing edges just by whether it's a solid line or a dashed line. It is clear from this figure that the serrated trailing edge is highly beneficial for reducing noise. For example, even when the flap isn't deflected, so the blue lines, for example, the serrated edges drop the noise by about 3 decibels across the frequency spectrum that they looked at, which means that the power is now halved in the sound. The same can be said for when the flap is deflected by about 10 degrees. But when the flap goes to even higher, to 15 degrees, and only at lower frequencies, do we see this drop in noise. At higher frequencies, we see the serrated trailing edge actually increases the noise by about half a decibel or so. The authors and other researchers suggest that this increase in noise is because the flow is severely altered by this extreme flap deflection, which must be the reason, but the exact change in flow physics isn't discussed here. Maybe we'll see it later on. Anyway, let's move on to figure 4, where we can see the vorticity being created by these serrated trailing edges. So in figure 4, we have A, B, and C. Figure 4A, this is when the flap isn't deflected at all. Interestingly, there isn't any significant vorticity being produced. The noise reduction seen in figure 3 seems to be just because the serrations at 0 degrees deflection changes the wall normal and span-wise pressure gradients. But perhaps we will see more results later on showing more. In figure 4B and 4C, we see the same general information, but for when the flap is deflected at 10 degrees. 4B is from the pressure side and 4C is from the suction side. Now we see the significant vorticity being produced by the serrations at this flap deflection angle. On one side of each serration, the vorticity is of one sign, and on the other side it is of the other sign, and it's opposite. So that is very expected because when you have a geometry with opposite sweep angles, this thing happens all the time. You effectively get 2 vortices, one on each side and one of each sign. And this provides insight into why maybe the flap is, when it's deflected at 15 degrees, the noise is not being reduced across the entire spectrum because the vortices grow to be so large and they impinge on the trailing edge, which then creates noise. That is very possible because anytime you have vortices hitting an edge, there is almost certainly going to be noise. Like if you look at even just airfoils, turbo machinery, anytime you have a vortex being formed and it hits an edge, that creates noise and often a feedback loop as well. So let's move on to figure 5 because we see the turbulence intensity plotted here. And again, I just want to point out another great feature of their plots. So they're using color bars where the colors used result in a linear change in how we perceive the information. So what I mean by that is that the color scale is linear. As far as we can tell by the human eye, it looks very linear. Contrasting that to other color bars, for example, the HSV one, which is a common color bar across softwares, for example, MATLAB or Python or whatever, the color that is green is in this HSV color bar represents so much of the entire color bar that it becomes difficult to actually distinguish the differences that fall in this green color. It can take up like 20 or 30% of the color bar. What that means is that minor changes at other points in the color bar equate to very different visual changes in color, hence making us think that the differences are far greater than what they actually are. Here, this linear color bar results in our eyes not being tricked by sudden changes in color. We attribute changes much more accurately based on the color. What that all means is that when we interpret the plots, it is far more accurate. Anyway, back to the actual information in this figure. So at 0 degrees, the turbulence intensity doesn't really change that much across the serrations. On the other hand, when the flap is deflected to 10 degrees, now we get turbulence intensities across the serrations up to like 0.15%. That is quite a big difference. And interestingly, even though in figure 3 we saw that the noise is being reduced by these flaps, the existence of this turbulence is actually going to produce some noise. So it's really a case of whether the noise that these serrations are reducing is greater than the noise that they are producing. And for these two flap angles, we saw that that is definitely the case. So in figure 6, we now see some really cool graphs showing literally where the serrations noise is coming from. So remember in figure 3, we saw that when the flap was deflected to 15 degrees, at higher frequencies, the noise was greater. Well, in this figure, we see exactly why now. On the left column, we see that the trailing edge with the serrations, when the flap is deflected at 15 degrees, a lot of noise is being produced at the edges here in this red. Comparing that to when the flap is at other angles, we don't get nearly as much noise being produced here. In fact, at 0 degrees, we even see quite a big drop actually at the very end of the trailing edge serration, at the tip here. So I personally think that at 15 degrees, the vortices are rolling up and hitting the trailing edge. That is what is producing the noise. From the data given, I can't quite prove that, but from figure 13, if we scroll down to here, we see some illustrations of how the air moves around the serrations. And on the pressure side, we see that the air flows around the serrations onto the suction side, and this is the rolling up process of this vortex, and very likely causing this noise because it's hitting the edges, and that's where this noise is coming from. So I think that as the flap angle deflects more and more, we get more and more air bleeding from the pressure surface to the suction surface, and that results in stronger vortices hitting the trailing edge and producing noise. Let's go back up to figure 7, and we'll see some other information before progressing. So figure 7, we see the pressures along the trailing edge of a serration. And in the top right of each subplot, this little region here in each one, we see a picture of the serration with these 3 dots on the edge. And one of the dots is filled in. These 3 dots correspond to the pressure sensors along this edge. And the filled in dot tells us that this sensor is the one that is given the data in this figure. Interestingly, the pressures seen on the serrated trailing edge at 0 degrees and 10 degrees are all quite comparable along the edge. But once the angle jumps 15 degrees, the pressure goes up too. So perhaps the formation of the vortices and the general flow of the air is nonlinear. I wonder what would happen if you were to deflect the angle even more by like 20 degrees to 20 degrees or 25 degrees. Perhaps an even greater jump would occur in the pressure. So over the last few figures, I think we have a pretty good idea as to why the flap at 15 degrees isn't as good at reducing noise as when it is at lower angles of attack, or lower deflection angles, not angles of attack, deflection angles. In figure 9, we see that the authors describe something called the streamwise and the spanwise correlation lengths along the trailing edge serration. Now this is a little bit of a cryptic description, but in essence, what these plots tell us is how big the flow structures are. The authors conclude that from these plots, on the pressure side, the flow features are longer because there is more correlation. As an extension, there is more interaction between these structures and the trailing edge. Now in figure 11, we see the sound pressure levels, so the noise, and this is plotted on the flat plate at a 10 degree deflection angle. It is very clear that around the edges of the serration, so just around here, we get quite a lot of noise occurring. And also at the trailing tip of the serration, we see a very large reduction. So here, look how blue it is, like a 3 decibel reduction, both on the suction side and even on the pressure side, perhaps. So with that, we come to the end of this podcast. We found that, okay, our wings are very good at reducing noise, these serrated edges, and we often hear that they just reduce the noise, but this study showed that they definitely are very good at reducing noise, but just adding serrations willy-nilly won't necessarily reduce the noise. What's more, there seems to be a sweet spot where the flow physics that the serrations create are strong enough to reduce the noise, but not so strong to effectively create even more noise themselves. So there is this sweet spot where you want to effectively create these vortices, but not so much turbulence intensity and not so strong vortices that when they impact the trailing edges, that will produce more noise. So with that, if you like this podcast, hit the like button. And if you want to see more like this, hit the subscribe or follow button, whichever platform you're on. And if you want to learn more about, if you want to learn OpenFOAM, either from the beginning stages or up to very advanced simulation methods like sliding meshes, dynamic morphing meshes, and even offset meshes, check out our courses. We have ones that take you through all the basics up to running your own DS simulations. And we have a course that goes from the advanced simulation techniques, which will leave you with even better CFD skills than most out there. And in both courses, we literally have master files that we give you. You can literally use them and plug in your own geometries and run them. So you don't even have to do all the legwork to set up these simulations. We have all the working files ready for you. You can find these courses in the link below. And if you do experiments like these peeps did here, did you know that you have almost certainly a 2 to 4% error in your data and you don't even know it? In the Atmosphere Hawk link below, we go through the math as to why, and you can check that out. And with that, we come to the end of this podcast, and see you next one. Peace, amigos.